Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, let us continue to discuss about the analysis and design of curved beams. In this lecture number 20, we are going to discuss about an application example of a crane hook. I hope you have followed the derivation in the previous lectures. So before you get into the application example, I wish that you should clearly understand the derivation of Winkler-Bach equation so that the application of that equation can be easily understood. So let us continue with the discussion, believing that you will allow this to remember and follow. So we already seen in the last lecture for a rectangular section, we found out the equation for modified area. This M is 1 minus R by A, B natural logarithm of R plus H by 2 by R minus H by 2, whereas for a given rectangle we know that the dimensions are b, and from the centroid this is plus h by 2 and this is another h by 2, and the centroidal axis is at a distance of r from the center of curvature. So, we know all these quantities are a, then h by 2 minus h by 2, I can get the modified area. Once I get the modified area, the location of neutral axis from the centroidal axis is given by a value E, which is mr by m minus 1, which we derived earlier. For rectangular section, we saw this derivation. Now, let us move on to revising or revisiting the circular section example. So, we said for a circular section, for the center of curvature being here and this being capital R and this being small r, we want to locate the neutral axis at a distance e from the centroidal axis. We said that m for a circular section, the modified area is given as 1 minus 2 r by r the whole square plus 2 r by r times of r by r the whole square minus 1. And once you know m, I can always find E as m by m minus 1 times of r. Let us look at this equation. I know r, I know small r, therefore I can find m. If I know m, I can find E. So, from the geometric property, I can always locate the neutral axis. Friends, that is very interesting. In curved beams, we do not require the stress distribution to locate the neutral axis. If you know the geometric properties of the cross section, you can always locate the neutral axis from the centroidal axis by this equation. Furthermore, let us continue this for another couple of cross sections which are commonly used in crane hooks. Let us take a T section. Let us draw the T section. Okay. Now, let us mark the dimensions of this T section as we see here. Let us say this broader breadth is B1 and smaller breadth is B2. And let us say if this is my center of curvature, and if I am able to locate my centroidal axis, I know this distance is always marked as r, the radius of curvature, and I call this point as r1 or this surface as r1, this surface as r2 and this surface as r3. Okay. So, now what I do, I select a strip at a distance y from the centroidal axis. Let that strip be at a distance v from the center of curvature and let the thickness of the strip be dv. Okay. So, this is my center of curvature. So, now we know the equation MA is given by integral y by y plus r d, okay, for the area E. So, now MA modified area is now given as y can be said as v minus r from the figure, please see that, and r plus y can be said as v. So, integral a dA. So, now I can split this as integral dA a minus r times of 1 by v dA of area A. Okay. So, now I can write this as A minus r times of, I can split this into two parts, integral r1 to r2 of b1 dv by v, because there are two pieces here. This is the first piece which is varying from r1 to r2. The second piece varies from r2 to r3. Okay. So, I am splitting this into two parts because the breadth is different. So, now I say b1 minus r times of r2 to r3 b2 dv by v. Now, I can say this MA is A minus r b1 natural logarithm of r2 by r1 minus r b2 natural logarithm of r3 by r2. Okay. So, therefore, M can be said as 1 minus r by a of b1 ln r2 by r1 plus b2 ln r3 by r2. Okay. Once I know M, I can find E as M by M minus 1 times of r. I can find E. Okay. Let us go for another cross section, which is an I section. So, let us draw an I section. Let us draw one more arm of this, which is slightly bigger. Okay. This is my I section. Now, let us mark the center of curvature for this geometry. Call this as OO, this line as O, and let me say this is the center of centroid of the system, which is at a distance r from the center of curvature. It is a central axis. Okay. I call this breadth as B1 and this breadth as B2 and this breadth as B3. Let me also mark these distances. Let us say this is at R1, this is at R2, and this is at R3, and this is at R4. Okay. Let me now cut a strip at a distance V. Okay, let the strip be marked at Y from the central axis. Let this distance be V and let the thickness of the strip be dV. Okay. We know the equation for MA. MA is integral y by r plus y of dA over area E. So, from the figure you can say y is actually V minus r by r plus y is V integral dA A, which is integral dA A minus r integral dA by V. Now again this is having series of rectangles, breadth B1, breadth B2 and breadth B3. The limits for B1 are R1 to R2, B2 are from R2 to R3 and B3 are from R3 to R4. So, let me add these rectangles separately and do it here. So, now I can write MA as A minus R times of integral R1 to R2 B1 dV by V plus integral R2 to R3 B2 dV by V plus integral R3 to R4 B3 dV by V. Okay. Now, let me integrate, say A minus R times of B1 natural logarithm R2 by R1 plus B2 natural logarithm R3 by R2 plus B3 natural logarithm R4 by R3 and so on. So, once I know MA, I can find M as 1 minus R by A of B1 ln 2 by 1 plus B2 ln 3 by 2 plus B3 ln 4 by 3. Okay. Once I get M, can always find E as M by M minus 1 into R, I can find E. So, friends, you get 3 triangles here, 3 rectangles here. Here there were 2 rectangles. So, I can also generalize this equation for n number of rectangles. So, general expression we also said as E equals R minus A by summation of 1 to n Pn ln Rn plus 1 by Rn. Okay, this is general expression for series of rectangles. Let us do a triangular section also. Let us say I have a triangle. This is the center of curvature. So, I can now say the centroid of the triangle is located here, CG axis, and let us say that is at a distance of R from here. Triangle has a base width of B1, okay, at a distance R1, and this is at a distance R2 from the center of curvature. Now, let us take a strip of distance of measurement x from here, which is at a distance y from the CG axis. Okay, and this strip is also cut at a distance v from the center of curvature, and let the thickness be d. Okay. Now, I want to find the width of the strip. Now, to find the width of the strip, I can always do a similar triangle exercise. X, this is B1. Okay. So, this is R1 and this is R2. Okay. Now I can write for R2 minus R1, I get for R2 minus R1, I get B1 by 2. I mean, I am talking about this. Okay. Now, if you want to find this, okay, if you want to find, let us say this value, I can say R2 minus V is equal to x by 2. So, can I find x? Okay, can I find x? X is going to be B1 times of R2 minus V by R2 minus R. Can I say that? Cross multiplication, right? So, B1 times of R2 minus V by R2 minus R1. Okay. So, if you want to find now MA, MA is given as integral dA minus R times of integral EA by V. We already saw this familiar equation in the earlier derivations as well. Now, I can write this as A minus R times of R1 to R2 B1 times of R2 minus V by R2 minus R1 times of dV by V. Can I say that? So, let us now say that is equal to A minus RB1 by R2 minus R1 times of integral R1 R2 R2 minus V of dV by V. Okay. So, which is equal to A minus RB1 by R2 minus R1 times of, let us say, R2 dV by V integral R1 R2 minus dV integral R1 R2, which is equal to A minus RB1 by R2 minus R1, R2 integral will be ln of R2 by R1 minus R2 minus R1. Am I right? So, now M is going to be 1 minus R by A R2 B1 by R2 minus R1 of natural logarithm 2 by 1 minus B1. Can I write this? Once I know M, I can always find or locate the neutral axis with E is equal to R, that is M by M minus 1 of A, M by M minus 1 of R, sorry, M by M minus 1 of R. So, which will give me R minus A by R2 B1 2 minus 1 R2 by R1 minus B1. So, if I know E, I can locate the neutral axis. Okay, friends, let us do this for a trapezoidal section. Let us say we draw a trapezoidal section. The cross section is a trapezoidal one. This is my vertical axis of symmetry. This becomes my O and this becomes my center of curvature. And we will now say this breadth is B1 and the top breadth is B2, that is away from the center of curvature, and we place this at R1 and we place this at R2, and if I locate the CG, I can locate this at a distance r from here. Let me cut a strip at a distance v, from here, and the strip is at a distance y from the centroidal axis. Let us say the width of the strip is x. Okay. From similar triangle, I can always find the width of the strip x. So, for B1 minus B2, this is R2 minus R1. For x, this is R2 minus V. Therefore, I can say x is given by B1 minus B2 by R2 minus R1 times of R2 minus V plus B2. Am I right? Please check this, friends. It is a basic similar triangle equation. You should be able to check this. So, I will write this x again. So, x, the width of the strip is given as B2 plus B1 minus B2 by R2 minus R1 times of R2 minus V. Okay. Now, we know MA is integral dA minus R integral dA by V. We already know this. So, let us do this. A minus R times of B2 plus B1 minus B2 by R2 minus R1 times of R2 minus R2 minus V, R2 minus V of dV by V, okay, minus B1 minus B2 by R2 minus R1 times of dV, which is from R1 to R2. This is also from R1 to R2. Okay. Let me write this equation again and integrate it. Let us say now MA is going to be equal to A minus R times of, let us say, B2 ln R2 by R1. That is the first integral, plus, let us say, B1 minus B2 by R2 minus R1 times of R2 times of ln R2 by R1. That is the second integral, okay, minus B1 minus B2, because if we substitute the limits, they will get cancelled, correct. Therefore, I get M as A minus R times of B2 plus R2 times of B1 minus B2 by R2 minus R1 times of ln R2 by R1. Okay, minus B1 minus B2. So, I can always find, this is MA, I can always find M, then I can always find E. Okay. So, now we have seen for different cross sections how the modified area can be computed using the geometric properties and fundamental derivation. Let us take up an example of a crane hook. We will take an example of a crane hook. A crane hook typically looks like this. Okay, looks like this. Let us say this crane hook has some central axis at which, and it has got also the center of curvature and a centroidal line. We know from the center of curvature the centroidal line will be always measured at R and the intradas is measured as R1. So, we call this value as 70 mm, okay, and let us say the R value is to be computed. Okay. So, we get the cross section of this hook like this. Say this is my OO axis, this center of curvature. Let us say this distance we know it is R1, which is given as 70. Okay. Let us say this dimension is 90 and this dimension is 30, and the CG of this we need to locate. We don't know this. This is the centroidal line. Okay, we don't know this. We need to compute this first, right? And of course, the depth of the section is known. The depth of the section total is 120. So, this is the cross section, which is, let us say 1 is 1. Okay. You will notice that intradas is having a broader width than the extradas because stresses are larger in the inside direction. We know that. So, first steps to locate the CG. I want to know this distance. I call this as x bar. Locate the CG. Let us draw this trapezium again. Center of curvature. This distance is given. This distance is given, and this distance need to be computed. We don't know this. Okay, I can always find this equation. X bar is sigma Ax bar by sigma I. So, I divide this into 3 parts, first part, second part and third part, and this dimension is 90 and this dimension is 30. I can always find x bar as half base height of the triangle, okay, and 1/3 of 120. That is for the first piece. I have 1 and 3 same, so I can say into 2 plus 30 into 120 into 60. This is for the rectangular piece. This is piece number 2. The whole divided by area of the trapezium of h a plus b. Okay. This is for piece number 1, this is for piece number 1 and 3, and this is for piece number 2. So, I get x bar as 50 mm. Please check this. Okay. If I have the x bar as 50 mm, then I will say the radius is now 120 mm. Am I right? 70 plus 50. Is it not? Now, let us write down the equation for the modified area for a trapezium. Modified area for the trapezium is given as 1 minus R by A times of B2 plus R2 B1 minus B2 by R2 minus R1 times of natural logarithm R2 by R1 minus B1 minus B2. This is the equation we derived. Okay. See here, trapezium, we derived the equation. We derived the equation. I am writing the same equation here. Okay, this is MA, so 1 minus RB, right? Let us substitute these values here from our problem. So 1 by RB. So R in my case is going to be 120. All are millimeters, friends. A is half H A plus B, that is area of the trapezium, which comes to 7200 mm square. From the figure, can you give me the value of B2? Please check. Can I say B2 is 30 and B1 is 90? And what is R2, friends? What is R2? Okay, let me write it here. R2, friends. Can I say R2 is 190? Let's see here. Because if this is 50, okay, this becomes 70 and this is 120 plus 70. Can I say R2 is 190? What is R1, friends? Is it 70? It's a given data. Okay. So let us check. I know R, I know A, I know B2, I know R2, I know R1, I know B1. Can you work out M? Please substitute and work out M. So M comes to be minus 0.080. Please check. Once you know M, okay, I can always find E. E is M by M minus 1 of R, which is minus 0.080 by minus 1.080 of 120, that is my R value, which comes to be plus 8.89 millimeters. Please check, friends. Okay, we computed, we allocated the neutral axis. So what do you mean by plus? The neutral axis shifting towards the concave side. Okay, it's coming here, right? This distance. I can even mark it in different color. So this becomes my neutral axis and this distance is E. It is moving towards the center of curvature, correct? So we got the value. Then I want to find the stresses. To find the stresses. So stress at intradas is given by minus M by AE HI minus E by RI, and at extradas it is plus M by AE H extradas plus E by R extradas. We already derived this equation, Winkler-Back equation. Now what is M in this case? M is the moment. Okay, M is the moment. It is considered to be positive. It is taken to be positive, okay, if it produces tension in intradas and compression in extradas. If it produces tension in extradas, for example, then it is taken as negative. If this is true, let us now see what is our case. Let us say I have a hook. Say this hook is carrying a load of about 10 tons. Okay, 10 tons, carrying a load of 10 tons. So now what happens? The moment which will cause by this, the moment which is causing by this, okay, will try to open the curvature. This moment will now open the curvature. So friends, as per our nomenclature, if it tends to close the curvature, it is positive. Therefore, M in our case will be negative because it is opening the curvature. So I can now say M is minus 100, that is 100 tons, 100 kilonewton into 120 by 1000, 120 millimeter. That is a center. I am trying to find out the moment at the center. Moment at the center, we know this is 120 mm. That is R. We already computed that. See here, we already computed that. Okay, 120. So I am taking moment about the center. So I am computing this. So this is going to be minus 12 kilonewton meter. Okay. Now, if you want to apply Winkler-Back equation, I want to find out the values of, because for this Winkler-Back equation, I need to know, let me write down here, I need to know M. M is minus 12 kilonewton meter. Okay, M is known. I need to know A. I have the A value. Okay, I need to know HI. What is HI in this case? HI is the distance of the intradas from the CG, right? This is HI, which is 50. So HI is 50. And what is HO, friends? Is it 70 mm? Because the total depth is 120 mm. What is E? Which is plus 8.89 mm. What is RI? 70 mm given. And what is RO? 190 mm. So in this equation, friends, all values are now known to me. I can easily find the stresses in intradas and extradas. Is it not? So let us try to do that. In addition, the hook will also be subjected to the direct stress. This direct stress will be tensile. See, the hook is getting pulled. The hook is getting pulled. When the hook is getting pulled, you'll have direct stress. Okay? So the direct stress, I can say the direct tensile stress is going to be P by A, which is 10 or 100 kilonewton, so many Newton, area is 7200, so I get plus 13.89 Newton per square tensile. Okay, now let us find out stress at intradas, which will be plus 13.89, and intradas, you know, the crane hook is subjected to a moment and moment is opening, therefore intradas will be in what? Tension or compression? Okay, the intradas will be in what? Tension or compression? What will be this value? Intradas will be this point, extradas will be this point. Okay, so it is opening up. So let us say it's going to be 30.89 stress at intradas, which we are saying as minus. So I should say minus. Let me write down the equation. which is going to be stress at interdas is minus m by AE HI minus E by RI. Okay. So, I am substituting these values here, minus m by AE minus of minus 12 into 10 power 6 by 7200 into 8.89 into HI minus 8.89 by RI 70, correct. So, this will become plus 13.89, okay, plus 110.10, so about 123.99 Newton per mm square tensile was positive. Similarly, let us work out the stress at extradas, which was given by plus m by AE HO plus E by RO. So, I want to find stress at extradas, which will be plus 13.89 tensile stress plus minus 12 10 power 6 by 7200 into this is E, okay, 8.89 of HO 70 plus 8.89 by RO 190. So, I get this as plus 13.89 minus 77.84, which is minus 63.95 Newton per meter square, which is compressive. Just look at the hook here. So, I have a crane hook, I pull a load, the moment is opening the curvature. So, if I take a point here, the point will be under compression. If I take a point here, intradas, it will be in tension, right? That is why we are getting here. Intradas tension, extradas compression. Okay. So, that is quite interesting. Now, let us compare this value with the straight beam equation. So, if I am using a straight beam equation, if I use a straight beam equation, stress is actually m by I into y. I for this section can be given as 7.92 10 power 6. You can work it out, it is very straightforward. Okay. So, now I can say stress at intradas will be 12 10 power 6 by 7.92 10 power 6 into 50, that is the distance of intradas from this EG, plus P by E. Okay. So, which is going to be plus 89.65 Newton per mm square. So, what exactly you are getting in intradas is 123.99, whereas you get 123.99 from the Winkler back equation. So, if you use the straight beam equation, you get 89. So, there is considerably a difference between the actual stress which is created in a crane hook vis-a-vis the straight beam theory. Okay? You will land up in estimating or underestimating the stress on this if you do not use the Winkler back equation. So, friends, let us come to the summary of this lecture. So, the summary of the lecture says that we have worked out the modified area factor for rectangle, circle, T section, I section, triangular and trapezium. Okay? We have worked out this. We have also done a problem of a crane hook subjected to some load P. We found out the stresses in extradas and extradas, and we realized that if we do not use the Winkler back equation, the stress computation will be wrong if I use a straight beam theory, and it will underestimate the value. So, there is a chance that you will end up in a wrong design. Okay? So, friends, I hope you follow this problem. More examples can be seen from the reference textbooks. If you have any queries, please post it to the discussion forum in SwayamPrabha. I hope you are enjoying these lectures of this course on maritime structures offered by Department of Maritime Engineering at IIT Gandhinagar. Any questions and any comments, please post it to us. Thank you very much. Namaste.